Hello everyone, and welcome back. We just finished our exercise on recurrent neural networks with time series, and as a quick bonus, I want to have a quick discussion on multivariate time series with LSTM recurrent neural networks. This is a often requested topic from students, so we'll go ahead and discuss it. So we have this quick bonus notebook. It actually comes after the exercise solution. So we're going to quickly discuss how to use LSTMs and recurrent neural networks to predict multivariate time series. Something to keep in mind, though, is that there's a few cons to using LSTMs for this approach. So as with all neural networks, the model is essentially a black box. That makes it really difficult to interpret what's the model actually doing internally in order to predict this multivariate time series. And that's a problem that extends not just to multivariate time series, but using recurrent neural networks for time series in general. It's essentially a black box, so you can't see what factors are important to the network, especially for a deeper and larger network, that actually relay information to forecasting into the future. Now, the larger con is time series is actually a very well-studied field of mathematics, and there's many well-studied alternatives that are actually simpler to use, such as SARIMA X or seasonal autoregressive integrated moving average exogenous models, and also VARMAX or VARMA-X models. So I would highly encourage people to check out those well-studied models first, and you can apply those not just to multivariate time series, but also single time series. And they work very well, and more importantly, they're very interpretable. So I highly recommend that you try those more conventional approaches before settling on LSTMs or recurrent neural networks for multivariate time series data or just time series data in general. While it can feel very cool to be using state-of-the-art recurrent neural networks for your time series forecasting, again, the con of not being able to interpret what's going on is a large enough con that you should really fall back to these well-studied ARIMA-based models. Okay, now fortunately, let's say you actually do want to check out recurrent neural networks for your time series data, and you happen to have multivariate time series. So there's actually only two real main changes you have to do to essentially the notebooks that we've been working with and the general structure we've been working with. So for a multivariate time series, the two main changes are the first, as you may expect, you may need to change the input shape in your LSTM layer to now reflect that two-dimensional structure. You may recall previously we had a variable called n_feature, and we were just setting that equal to 1, since we just had a single variable or a single feature in our time series. In order to reflect a multivariate time series, we'll simply change that to however many features we have in that multivariate time series. And then the second main change is that final dense layer. Previously, it was just one neuron because we were just forecasting a single value into the future. For a multivariate time series, we're forecasting multiple features into the future. So we'll need one neuron per feature or variable. So let's go ahead and explore these changes. Since essentially everything else stays exactly the same, we're not actually going to manually program through this bonus notebook. Instead, we'll just go ahead and walk through and point out where the two main changes happen to occur. Okay, let's open up that notebook and walk you through it. Okay, here we are underneath the RNNs folder. At the very end, you should see bonus multivariate RNN. And if you don't see it, make sure you've downloaded the latest version of our zip file. Let's go ahead and open up that notebook and basically just walk through the major changes. So we have a little warning here that basically tells you that you should definitely check out these ARIMA-based models before jumping to LSTM. But let's imagine that you do have a multivariate time series and you do want to forecast these multiple variables into the future. So what we're working with here is a multivariate time series that essentially it's a data set that occurs a recording every 10 minutes from a wireless sensor network. So this wireless sensor network is actually recording a bunch of different features, and it's every 10 minutes for 4.5 months. As you can imagine, recording something every 10 minutes for that much time, 4.5 months, it basically creates a huge data set. So later on in this notebook, we're only going to take part of that data set because we want to forecast 24 hours into the future. We don't need 4.5 months of information at 10-minute intervals to learn that behavior. So we'll go ahead. We actually have here linked the original source of the data set. Let's zoom in a little bit. Again, we're not actually going to code this notebook out manually, and so we'll just walk you through it. So let's get just a little bit of a better view. I'm going to toggle the header here so we can really focus on the code. So first things first, I did my imports and I read in my CSV file. I set infer datetime format equal true, so we can actually infer here that not only is this date stamped, but it also has a timestamp. And then we set the index column to the date there. So if you run that line, you should see something that looks like this, where you have this index called date, and they're date time objects. Date time because not only are there the date, but you can see it's every 10 minutes, it's a recording of how many appliances are on, the lights, and then these various features. And you can check out more information about those various features in the actual description and link here below. So we have all this variable data that was recorded. And what we want to do is, theoretically at the end, I want to forecast all these multiple variables together. So you can see the information here. Luckily, I'm not missing any information, so non-nulls. And then if you want, you can explore the various features themselves. So here we can see wind speed, and here we can see appliances, etc. Notice it looks very noisy, and the x-axis overlaps because these are 10-minute increments for 4.5 months. So there's tons and tons of data points here. Okay, so clearly there's some sort of behavior because you can see here looks like there's empty spaces. So we can imagine things like occurring during night or occurring on the weekend that could change some of the use cases. So what we do is we're going to do a train test split just as we did before. But before that, since we're only predicting 24 hours into the future, so as noticed here, since we just want to predict 24 hours into the future, we don't need 3 months of data. So what we're going to do is save a little bit of training time, and we're just going to select the last month's data. So if we take a look at the head here, it starts at 2016, 01/11, and then goes to 2016, May 27th, so 05/27. Let's just go ahead and say grab the entire month of May. And we can do that with .loc by saying starting at 2016, 05/01, and then go all the way to the end with a colon. So that just grabs essentially the month of May, going from the 1st all the way to the 27th. Optionally, if you want, you can use all the data, but you'll save some training time by just grabbing that chunk of the data. So we got May, we went ahead and reset our data as that. And what I also want to do is you'll notice that it has really high precision, but a lot of this is unnecessary. So we can see here it has lots of zeros. And for such high precision, especially after we normalize the data, it's not going to be helpful to the network. It's essentially just going to be noise. So what we'll also do is we round off the data to either 1 decimal point or 2 decimal points. It's really up to you. So here we went ahead and said df round to 2. And the next thing is to figure out, well, what should our batch sizes look like? If there's 10-minute increments that this is being recorded, we know there's 24 hours in a day, and then there's 60 minutes per hour. So divide that then by 10, which means every 144 rows is 1 day of information. So you can imagine that if I wanted my test range to be 2 days, so here we have this little variable that you can play around with, test days is 2, then I just multiply that by 144 to get the actual amount of rows. So here we have this little test index that represents how many rows back I'd have to reach in order to have my test set at the end be equal to this many days. So 2 times 144, that means the last 288 rows represent those last 2 days of information. So setting that as my test set, what I can do is just use this integer-based location by saying starting from the beginning colon all the way up to, but not including, negative test index, essentially minus those 288 rows as my training set. And then the test set is starting from the end and going back negative 288 rows, colon, all the way to the end. So notice that minus sign in the indexing. It won't work if you try it the other way around. Okay, so now we have our training set starting at May 1st, going all the way to here, May 25th, and the test set starting at May 25th, just 10 minutes later, and then going all the way to May 27th. Perfect. Then we'll go ahead and scale our data, just as we did before. We only do it on the training data. We don't want to assume prior knowledge of this test set. And then we transform both train and test to get the scaled versions. The time series generator object, this is what we did before, very useful to us. So we import it just as we did before. And notice here, I set my length to 144. So I want to get that full daily cycle in the length. So that's a logical choice. Batch size, that's still equal to 1. And so this essentially looks the same as before. Scaled train, length, and batch size. The only thing you can play around with here really is the length. And 144, it's logical since that's a full day's information for the batch. So given 1 full day, go ahead and tell me in the forecast what the next 10 minutes are going to look like. Okay, so we have the length of a scaled training set. We know what the generator does. However, if you take a look at the first batch, you'll notice that it's quite a bit larger because the first batch is now essentially passing in every single column, and you have a multivariate time series. So these batches are a lot larger and a lot more complex. but the same idea holds, that given these last 144 data points for each of the feature columns, show me and predict the next 10 minutes worth of data, essentially one row into the future of all those variables. So that's why Y is so large. It's one Y per feature because it's a multivariate data set. Okay, so you can edit the length so that it makes sense for your time series. Then we create the model just as we did before. And this is where the first change occurs. We have this LSTM layer here. The input shape is going to be again defined by the length of that batch, comma, and then scaled train dot shape of 1. So what is dot shape of 1? Well, if we take a look at the shape of scaled train, currently it's 3,565 rows by 28 features. Where 28 features, that's just the number of columns we had in the original data frame. So if you scroll all the way back up here and take a look at our original data frame, and you take a look at these 28 columns, we're right now predicting each of these columns 10 minutes into the future, step by step. So this is what makes it multivariate, is that instead of just predicting, for instance, appliances into the future, we're predicting these 28 columns into the future. So that is kind of main change number one that you have to take into account, is when you're creating that model, the shape here for this second dimension, the input shape, has to reflect the amount of features you're considering. And I've actually put it here as scaled train.shape index 1 because this is now the generalized version of any other data set. So you could import your own multivariate data set, check out the shape, and you still be able to use this code and just plug and play because this is the generalized version. And same, the second change here is the final prediction layer. You should have one neuron per feature, so it should be the dense layer of scaled train, again, .shape 1. So if you wanted to, you could hard code these as 28, but here we have the generalized versions. And those are the two main changes you need to consider when dealing with multivariate data. And as mentioned in the lecture, I would highly recommend you check out ARIMA-based models first because of their interpretability, and they actually perform very well on multivariate data sets. So you can check that out. After that, you get a summary of the model, and you can also implement early stopping if you want, just as we did before. Essentially nothing changes here. It all looks exactly the same. And then we just fit to that generator. We choose some amount of epochs. We can do early stopping. We only train for 2 epochs because, as you can imagine, dealing with a multivariate data set, your training time is going to go up quite a bit. So you'll notice here we only train for 2 epochs, and it was still taking about 8 minutes per epoch, more or less. And if you only train for 2 epochs, there's still plenty of room for improvement. You can see both training validation, the loss on both training set and your validation, that test set, we're still going down. So this probably could have trained for a lot more epochs. So early stopping was actually never hit. So you can go ahead and play around with that data set and then train it for longer if you have the patience for it, or if you have some free time to just let your computer run and crunch those numbers. Then the evaluation, all of this code is essentially exactly the same as before. The only things you need to consider here are when you're reshaping those evaluation batches, it's 1 by length, and then here it's again scaled train dot shape 1. So that's the main difference here, because now that first batch has to include those 28 feature columns. So that's during the evaluation. And then here, you'll notice that we're essentially just going to set n features equal to scaled train dot shape 1. For all our previous problems, the number of features was just hard-coded as 1. But here, we want to make sure it equals to the same number of feature columns we had in the beginning. And then that loop is exactly the same. And here we're just predicting for the test range. We could just expand that number to forecast into the future, especially if you just retrained on everything. So all this code, pretty much exactly the same. The main thing to keep in mind here is your number of features is going to be higher than just 1. And then here we have the test predictions, scaled tests, and if you want, you can inverse those transformations and begin to compare. And here we have the real test data versus our true predictions. And you can see our true predictions are a lot noisier, and there's definitely room for improvement here. Now, again, it really depends on the actual situation for how you would actually evaluate this model. You could do root mean squared error, but recall that you have all these features. So what you could do is do a root mean squared error, comparing, for instance, appliances versus the true appliances prediction and see how that performed. If you just are concerned about your root mean squared error on appliances and your forecasting capability on that particular feature. But if you're forecasting on everything as a whole, maybe you want to do some sort of weighted average of your root mean squared errors across all these features. It really depends on what features are important to predict, which features are not that important, and also you'll notice that the scale here is different for all these. So it'd probably make more sense to start calculating that sort of error term on maybe the scaled version. Again, it really depends on the exact situation and your exact data set on how you should be evaluating these multivariate predictions. Okay, but again, the main differences here are during the forecasting section is edit the number of features here, and during the construction of the model to edit the number of features in this simple RNN layer to reflect that input shape, and then one dense neuron, or one neuron in this dense layer per feature. And those are essentially the main changes. Okay, I hope that was helpful to you. And as always, again, I would highly suggest checking out those ARIMA-based models first before jumping into this kind of black box of deep learning. But this notebook is here for you in case you want to use it. Thanks, and we'll see you at the next section of the course.